Long before we asked how large the universe is, it was already at work. Mountains lifted and wore away. Forests spread and vanished. Deep time settled in layers of rock beneath a thin surface we call history. Stone rose into continents and oceans gathered. Life stirred in darkness and endured across ages of fire and ice. Rewind further, and Earth dissolves into molten light. Before that, stars emerged from collapsing clouds, and before the first stars, there was only hydrogen drifting in darkness. Before all structure, the universe was hot and dense. To ask whether it is infinite, we travel backward from life to stone, from stone to starlight, and from starlight to the first expansion of space. How large is the universe? This question leads naturally to a necessary distinction between the universe as a whole and the observable universe. The total universe includes everything that exists, whether visible to us or forever beyond our reach. The observable universe is more limited. It is the region from which light has had time to reach us since the Big Bang. It forms a sphere centered on the observer, bounded by the cosmological horizon, and reflects a universe approximately 13.7 billion years old. At first sight, it is tempting to imagine that this sphere has a radius of 13.7 billion light-years. That would be true in a static cosmos. But our universe is not static. Space itself expands, and this expansion reshapes our intuitive understanding of distance and time. Since the Big Bang, space has been stretching. According to Hubble's law, the farther a galaxy is, the faster it recedes from us. Expansion was even more intense in the early universe. As a result, the most distant regions whose light reaches us today are not 13.7 billion light-years away, but about 46.5 billion light-years away. The observable universe therefore spans roughly 93 billion light-years in diameter. This does not mean that light traveled faster than light itself. When that ancient light began its journey, those regions were much closer. Over billions of years, the expansion of space increased the distance between us and the sources of that light. In fact, some galaxies today recede from us faster than light. This does not violate relativity because they are not moving through space at superluminal speed. It is space itself that expands, carrying galaxies with it. The universe expands to such immensity that its horizon is no longer a boundary but a fading line. Seeing is not the same as reaching, and beyond a certain distance, the universe stops being distant and becomes forever untouchable. There is a deeper boundary than the edge of what we see. Beyond a certain distance, the universe does not merely appear far away. It becomes permanently unreachable. This limit is called the cosmic event horizon. It lies today at roughly 16 billion light-years from us. Within it, light emitted now may still find its way to our telescopes given enough time. Beyond it, something more final occurs. Even if we could travel at the speed of light, we would never arrive at those regions. Their present state is already lost to us. Photons emitted there today will never overcome the expansion of space. The distance between us grows too quickly. Space stretches faster than light can bridge it. What lies beyond that horizon is not empty. Galaxies continue to shine, stars continue to form, and structures continue to evolve. But their current reality will never intersect with ours. And this boundary is not static. As cosmic expansion accelerates, more galaxies slip beyond it. Over billions of years, the deep sky will thin. One by one, distant systems will fade from view. In the far future, only the galaxies gravitationally bound to our local group will remain visible, isolated in a darkening cosmos. The event horizon marks not the edge of existence, but the edge of connection. Beyond it, the universe continues. Yet for us, parts of it are already gone forever. There is no physical edge waiting in the dark. No wall, no boundary, and no abrupt end. If we could somehow travel to the farthest limit of what we see, we would not encounter a frontier. We would simply carry our horizon with us. The observable universe is not a structure suspended in space. It is a measurement defined by time. Its radius is not a wall, but a duration written in light. A civilization in another galaxy would measure a universe of the same radius, centered elsewhere, watching a different portion of the same vast reality. Beyond what we currently observe, there is almost certainly more universe, more galaxies, and more structures from which light has not yet had time to arrive. The boundary we perceive is not a physical barrier, but a limit imposed by the finite speed of light. The edge of the observable universe is therefore not the edge of existence. It is only the edge of what has had time to reach us. If there is no edge in space itself, then the real question shifts. Not where the universe ends, but whether it ends at all. If what we see is only a portion, then does the rest continue without bound? Beyond the limits of light, does space stretch forever, or does it remain vast yet finite in ways we have yet to detect? Does the universe end somewhere beyond the reach of light, or does it continue without bound? The answer depends on the geometry of space itself. At the largest scales we can measure, the universe appears remarkably flat. Light travels across vast distances without revealing any detectable curvature. Patterns in the cosmic microwave background suggest that space does not visibly bend back on itself within the limits of our observation. If space were perfectly flat everywhere, then the universe could extend infinitely in all directions. In such a case, the observable universe would be only a finite region carved out of something boundless. Yet flatness at our scale does not guarantee infinity. A surface can appear flat when examined locally, while still curving gently over immense distances. The observable universe, vast as it is, may still be too small a sample to reveal the full structure of the whole. What we know is this: if the universe is finite, it must be far larger than what we can see. Why? Because every measurement we make of cosmic curvature tells the same story. Space, at the largest scales we can observe, appears almost perfectly flat, and a universe that looks flat across 93 billion light-years cannot suddenly bend sharply just beyond our view. If it curves at all, it must do so gently, over distances far greater than the observable sphere. Current measurements therefore imply that the total cosmos is at least hundreds of times greater than the observable region, and possibly millions of times greater. The margin of uncertainty is enormous. Infinity remains a possibility, not a conclusion but an open horizon. Beyond the limits of light, space may continue endlessly, or it may curve in ways too subtle for us to detect. For now, the question remains suspended between mathematics and measurement. If the universe is truly infinite today, that possibility extends backward to its earliest moment. The Big Bang describes the expansion of space itself, unfolding everywhere at once. There was no outside into which it expanded, no central location from which it began. In an infinite cosmos, the early universe could have been compressed and hotter yet already without edge, its vastness present even in its most extreme state. Expansion did not create space beyond a boundary. It altered the scale of what was already there. Distances grew, temperatures fell, and structure emerged. The universe did not unfold into something larger than itself. It changed its proportions, carrying galaxies apart as the fabric of space stretched between them. If infinity is real, then the beginning did not occur at a place. It occurred everywhere. Every region of space, however distant, shared the same early fire. The density was universal, the temperature shared, and the expansion common to all directions at once. In such a picture, the Big Bang becomes less a moment in a location and more a condition of the whole. An infinite universe would not have grown from a point into vastness. Vastness would have been present from the start, compressed into a state beyond imagination. The unfolding of cosmic history would then be the story of expansion within an already boundless stage. And if that is so, then the question of infinity is not only about size, it is about perspective. The observable sphere becomes a local window into something that may never terminate. Our measurements trace a finite arc, yet the underlying reality may extend without edge. Whether the universe is infinite or merely unimaginably large, the consequence is the same. What we see is only a fragment of a structure whose full extent may remain forever beyond comprehension. Across this vast uncertainty, one fact remains quietly stable. Every horizon is drawn from somewhere. The observable universe is centered on us not because we are central, but because observation requires a point of view. Move elsewhere, and another sphere unfolds. Change position, and another sky defines itself around a different observer. In a cosmos that may extend without end, perspective becomes the only boundary we truly possess. Distance expands, structure evolves, and light travels across incomprehensible scales, yet meaning always gathers locally. Whether the universe is infinite or simply beyond measure, the consequence is similar. We inhabit a finite window carved from something far greater. Our instruments map what light allows. Our theories extend that map through inference and mathematics. Beyond that lies possibility. And within that possibility stands Earth, a small world orbiting an ordinary star in a peripheral arm of a single galaxy among hundreds of billions. From a cosmic perspective, it occupies no privileged coordinates, no geometric center, and no preferred direction. Yet on this fragment of rock and water, matter arranged itself into life, and life arranged itself into thought. Oceans reflected starlight long before they reflected consciousness. Continents drifted, climates shifted, and species rose and vanished until one form learned to measure distance in light years and curvature in background radiation. In a universe that may stretch without end, Earth remains local and finite, bound by gravity and atmosphere, yet capable of conceiving scales that dwarf it. If infinity is real, then our planet is not the center of the whole, but a point within it, where the whole becomes aware of itself. Its significance does not arise from size or position, but from understanding. On this narrow surface suspended in vastness, humanity did more than look upward. It learned to exceed the infinite in thought before ever reaching it in space. Mathematics revealed infinities within numbers. Physics uncovered horizons within equations. From calculus to cosmology, from the continuum to the multiverse hypothesis, the human mind discovered that infinity is not only a property of distance, but of structure. On this small world, finite in size yet boundless in abstraction, the infinite first became a concept, then a calculation, and finally a measurable frontier.